Hello everyone, welcome back to Exploring Quantum Physics. I'm Charles Clark. Now we're going to start to use some of the tools we've developed and get a glimpse of how they're applied in larger, scalable calculations, in particular those that use some form of the variational principle. Now, in the quiz at the end of the last lecture, we looked at this function. It's a generalized Gaussian exponential of a quadratic form, and you have seen you've seen the one-dimensional version of this previously. This is the notation that I prefer because I can remember it, and I write it out here because it illustrates an important thing, and that is in the Gaussian, there's a scale parameter, which is a length scale parameter d. And that means for when in the regions where x is much greater than d, psi goes rapidly to 0. So this d describes a localization domain of the wave function. And also leads to an important observation on the dimensional units of the wave function, which I offer you to consider in the online quiz. So the dimensional units of the one-dimensional wave function psi of x is it's 1 over the square root of length. I mean, I find a common misconception among beginning students of quantum physics that the wave functions are all dimensionless. Well, they're not. And in fact, that has very important consequences for making estimates. The wave function is a proxy for the probability density, which has the units of inverse volume. So be aware. And there's a problem in the homework that where this aspect comes up. Now, I put a lot of emphasis on the use of Gaussians just because there are ways of remembering what to do that are very conveniently exercised by use of Gaussian trial functions. But secondly, they are a tremendously powerful influence in theoretical chemistry, that is, the calculation of molecular structure. And this man, John Popel, is a person who's is awarded the Nobel Prize in Chemistry primarily for developing Gaussian-based techniques of the calculation of structure of complex molecules. And just as an example of how influential this approach has been, here are some citations of articles that deal, just simply with the properties of Gaussian basis sets. So over 14,000 citations of this article, and you can compare that to what, at least as of a year ago, was the most cited paper in physics, probably still is, the paper that articulated the standard molecule. There's just probably there are many more chemists using these type of approaches in a large-scale way than there are physicists. Now, why are these trial functions so powerful? The answer is the variational theorem, which we're going to prove briefly. So I'll state it this way, and this is not a rigorous math statement. It's kind of like a physics statement. So if we take any Hamiltonian, that means any Hamiltonian with reasonable properties, and any normalizable eigenfunction satisfies that condition, then the expectation value of the Hamiltonian over that wave function is greater than or equal to the ground state energy of the system. And so that means if you just have a big gun and lots of bullets and some intelligence, you just take a large set of functions that you can systematically expand, and start varying and do a random walk through function space to try to lower the energy of the system, and you will, with luck, you will approach the ground state energy that you seek. The ground state energies are important, particularly in things like molecular structure, in the sense that the ground state energy of the lowest energy electronic wave function, if you consider the dependence of the total energy of the system on the nuclear coordinates, it's usually effective to find that by minimizing the electronic energy subject to variations of the trial functions. Okay, let's see how that works in practice. Well, no, let's see how that works in... So here's an outline of the proof of the variational theorem. I just restate it here from the previous slide. Now, you might want to... I'm gonna go quickly through from one step to the next, but you might want to pause the lecture and make sure that you understand the procedure, because this is actually emblematic of a lot of arguments made in quantum mechanics. So, let's see, I should have written this as a psi like that. Let us say that we know in principle all the eigenfunctions of the Hamiltonian. So I mean H hat phi n equals E n phi n. There exists some eigenfunctions, even if we don't know them. They form a complete set, so we can whatever the trial wave function is, it can be expanded in the basis of eigenfunctions that satisfy this. Well then, what's the expectation value of psi? Well, we can just compute it straightforwardly within this representation here. So we just plug that part in. Well, let's see. This part here is identically equal to that, and then this one is its Hermitian transpose. So this is just a straightforward representation of how we calculate the expectation value of the Hamiltonian. And so now, by construction, phi m h hat phi n equals delta nm, because they're eigenfunctions. So that just collapses this two-dimensional structure into one. And now this sum must be greater than or equal to the same sum where instead of taking the state-by-state energy, we take the common, the ground state energy, E naught, and then this sum is just E naught. So in other words, this term, this is proven that the average expectation value of the Hamiltonian is greater than the ground state energy. And in fact, the equality sign means that if psi h psi equals E naught, then h psi equals E naught psi. So it happens to be, if you get an equality, you have found a ground state eigenfunction. Now, as to why this is important in practice, and in chemistry in particular, I don't think we're going to cover this topic in any detail in this course, but if you Google or go to Wikipedia and look at the Born-Oppenheimer approximation, you'll see there's this general argument. Electrons move much faster than nuclei, and so in a complex material system, the nuclei are moving slowly, and the electrons are able to adjust essentially instantaneously to motion of the nuclei. So they electrons are sort of the glue that holds materials together. So if you can minimize the total energy of the system for fixed internuclear coordinates as a function of the electron wave functions, then you typically get a very good representation of the material structure. And this task was made conceptually and practically much easier by Walter Kohn and his collaborators, who got the Nobel Prize in Chemistry for the development of density functional theory, which is now sort of one of the practical theoretical underpinnings upon which a Gaussian trial approximation is used. So just to summarize, these things are very useful for a lot of applications, and you're going to make an application of it in one of the homework problems.